Hi guys, welcome to the next lecture in this Python for Aerospace Engineers. That's what I'm calling it this week. We went through a lot of stuff quite quickly a couple of weeks ago, and you've had 2 weeks to go through those lectures or the exercises that are contained therein. There was a lot in there that I didn't necessarily think you would fully understand the first time through, and that's fine, and that's not because I think it's beyond you, just because at this stage of your careers you won't necessarily realise the context of some of the things that you're going to be using. What I hope is that you complete these exercises and you've got these Jupyter notebooks somewhere that you can then think, in 2 years' time, oh, I need to fit a line through some data, and I'm going to remember that I went through that with Professor Smith, and I've then got a repository of all of those informations, and you can use that for whatever you go on to in your later studies. Similarly, this bit that we're going through today is a continuation of the aerofoil information that we started in class. We're actually going to use some of the techniques that we went over in the previous video in terms of curve fitting to try and do something kind of smart. We're going to try and take some aerofoil data and see if we can work out what NACA 4 series it comes from. So just to remember what we went over in class, we went over the sort of definition of aerofoils. So we're looking at this two-dimensional cross-section through a wing, and we said that aerofoils have an upper surface and a lower surface. So this was upper and lower. We said the chordwise direction was X, the vertical direction is Y. So we are looking today just at this sort of normalized aerofoil, one that goes from 0 to 1. Okay, I'm going to leave it as an exercise for you guys to figure out how to scale this if you want to. We can just multiply it or divide it by a number to make it bigger in both directions. And we said that there was the NACA 4 series that we looked at that was defined by the Camber Line. So there's a polynomial that describes the Camber Line. And then some sort of polynomial that defines the thickness. Now, I could go through and write those out on the board for you, but actually that would just be a lot of writing for something that I don't necessarily want you to copy down, because I'm going to give it to you. So I've got in the description of this video and in the Slack space is the start of this workbook. So let's bring that workbook up on screen and get rid of this aerofoil, or move the aerofoil up here. I'm experimenting with trying different video techniques where I can appear behind my text, so I can sort of point at things a little bit better. If you like or don't like this, let me know and we can figure out what's the best means to get this information across. But what we've got here, this is an introduction. This is a Jupyter notebook that we're going to be using today, and in here is contained the information that describes how the NACA aerofoil, the 4 series, is created. So we start out with the 4 numbers, M, P, and then TT, where TT is 2 defining the thickness. M is the maximum camber in percentage, so the displacement of that camber line from the horizontal axis. The P is the location of that maximum camber, which is in tenths of chord, and then the thickness ratio is the last 2 digits. Again, this is in percent. It's worth noting, and I've included it in here, so you guys can have a look at how to edit this. So if you double click in this cell, it's a markdown cell. You can have a look at how some of these equations are put together. This is using what's called LaTeX formatting. LaTeX spelled with an X, so LaTeX. And I trust you guys to be able to Google that safely. You can look at how to input sort of some fancier equations. But what I'm going to put in here is that thickness is given by this, and the location of maximum thickness is 30%. For these aerofoils, and that's going to be useful because we're going to use that to work out what a given aerofoil is given some data. So let's do this. I think we should take an aerofoil, let's say 2309. We're going to take a 2309 aerofoil and we're going to see if we can plot it. So we're going to do that through developing some functions. That's going to help us, and we're going to I'm going to make, in fact, let's do this all as a function. Let's produce a function called NACA 4 that accepts a number and then plots it. So we're going to do this all from scratch. let's say def NACA 4, and then I'm going to input the aerofoil number, so number, and let's default it to 2309. Okay, and then I'm going to put in a number of points that I'd like to plot as well. So remember that these aerofoils are defined by continuous curves, but on computers we can only input a finite number of points. So let's say we'll default to 500 points. So that's my function defined, and anything that's then now indented exists within the function. Anything that's not isn't in the function. So let's give this what's called a doc string, and we'll say what we'd like it to do. So I put 3 quotes, and it will give me the 3 end quotes when I do that. And I'm going to say we want to plot a 4-digit NACA aerofoil given a 4-digit input string. So inputs. I can't talk when I'm doing some of this. I've just put in a bit of a description about this function, and then at the moment it doesn't really do anything, but we can see that this will appear if I do help NACA 4 now, because I've run the cell. I've run this cell, so now if I run this, the function exists. It now gives me some information about it. So here we go. It tells me what it does. This isn't necessarily formatted quite how it should be according to certain Python practices, but it's good enough for an engineer to work with. Okay, so we're going to do some things now. We're going to get those numbers out. So remembering up here we've got MPTT. We're going to get those numbers out when they're input in here. Okay, I can't point there, but when they're input in here. So let's say that M is equal to, so this is a string. The default value is a string here, so I'm gonna, let's just test something down here. Let's say my string is equal to hello. So I can get items out of a string just by selecting their index using square brackets. So I'll say first letter is equal to my string. And then I'm going to do print first let. Okay, so this is helpful because this enables us to pick those digits out. So because this is input as a string, I can say M is equal to a float because I actually want the number back. So I want the first digit, and I'm going to then want to divide it by 100. Okay, so that's going to give me the thickness as a decimal because the first number here. So this is it's 2. I keep saying thickness. I shouldn't have said thickness. The position of the maximum camber is here now. So this is being input as 2. Okay, so the position of the maximum camber. Oh, sorry, not the position of the maximum camber. I'm going to go back and re-record this. So let me start again. So this number that I'm getting out now is the maximum camber of this aerofoil. So this is going to be 2%, so I need to take this number out, divide it by 100, that's giving me the number as a decimal. And now the position just comes from the second one, so I can do the same thing. So I now want the second digit, I want to divide it by 10. This gives me the location of the maximum camber. Okay, and then T is going to be the thickness, so I then can just do T is equal to the float of the number that goes in, 2 to the end, divided by 100. So we can just test if this function is working. Let's just do print. We'll say NACA number has max camber of m 1.3f at p 1.2f with a thickness of t 1.2f. Okay, so if I run this now, I've redefined the function. It hasn't done anything yet. So if I go down here and just try and do NACA 4 with no inputs, it's going to run it and it will take the default of 2309. Okay, and it tells me NACA 2309 has a maximum camber, and these are all decimal values of 0.02 at 30% with a thickness of 9%. Okay, this is exactly what we expected to have. So that's good, and we don't necessarily have to print this out each time, but it's just helpful whilst we're running this code that we can sort of debug it this way. Let's think about what happens if I now put another, let's put another one in. Let's say I want a 0012, most famous aerofoil in the world. There we go, maximum camber of nothing at 0 with a thickness of 0.12. Let's just try this here actually. Let's say, because this is obviously a symmetric aerofoil and it makes no sense to print out these numbers. So let's say if m equals 0, let's just print out that it's symmetric instead. So I've just, at the moment I haven't changed what the string has said. I just said that if m is 0, i.e. it's symmetric, then we'll say get rid of these first two bits and we'll say is symmetric. That doesn't work. Oh, because I haven't rerun it yet. I've just redefined it. Now let's run this. NACA 0012 is symmetric with a thickness of 0.12. Okay, let's just think about what else we could do. Maybe I don't want to input a string. Maybe I'll just input 0012. See if this works. Doesn't work. Okay, so it's not going to work because it won't work when you input a number like that. So numbers aren't allowed to have leading zeros, so we have to put a string in for this. Okay, so we've got this first bit now. We still haven't done anything, so let's try and let's see what we can do in terms of plotting it. So we're going to need NumPy for this. So let's import NumPy. NumPy as np, and we're going to import matplotlib. Imports matplotlib.pyplot as plt. Okay, so let's now use one of these equations. The first thing we want to define is the Camber line. Okay, so we're going to take this equation. Let's there's no easy way for me to have these both up on screen, I don't think. Let's write this equation down. Tell you what, I'm going to do this. I'm going to take a screenshot of that and then load the screenshot on my iPad and move it down, which is kind of a silly way to do this, to do some major editing of this video. Okay, so what we want to do is we want to better work out this equation. So what this is saying is if we've got a position of maximum camber, which we know for this one is, let's go back to running this with NACA 4 with no inputs, say is at 30% for this one. So we want to make a vector that goes from 0 to 1. That's going to be our vector that goes, our x vector. So this is going to be, say, 0, 0.1, 0.2, all the way up to 1. We're going to use slightly smaller steps. We're going to go in 0.01. But that's what our vector is going to be that defines the x. And then this one here defines the corresponding camber. So in here, we're going to say, once we've got down here, the next thing is to do, we'll say we'll define and x chordwise. And I'm going to put in brackets, this is normalized. things goes from 0 to 1. Rather than going from the actual dimensional chord value, we're going to go from 0 to 1. So I can say that x is equal to np.linspace 0 to 1, and I'm going to go in steps of n, where n is defined in the function itself. So I've then got that array, and I can then do this equation up here, and I'm then going to say if I'm behind the 30% thickness line, I want to use this equation. If I'm above the 30% chord line, sorry, I said thickness, I meant chord line, then I'm going to use this equation. So I'm going to come up with a function for a sub-function within here for my camber line. So I'm going to say def camber line. So it needs to be a function of x, which is the distance along the x-axis, and then it also needs to be a function of m and p, because that's what exists up here. So I'll have m and p, and we'll then say, well, I know I'm going to need to do it in two chunks, this bit that's ahead of 30% chord and this bit that's after 30% chord. So I'll just make an array that's the right size in the beginning. So I'll say yc, which is my camber line, is equal to np.zeros, and I'm going to make it equal to the size or the shape of x. I'm then going to say, well, at all positions where x is less than p, which is the position of the maximum camber, remembering that this is just a decimal and we're going from 0 to 1 in x, I want to use this first equation up at the top. So it's m multiplied by x, but I need to specifically say x where x is less than p here. Okay, so that's m times x divided by p squared multiplied by 2 times p minus x where x is less than p. And I don't need to divide by c because I'm doing this is the equation for a dimensional camber line. I'm doing everything in this non-dimensionalized normalized format. So this is the equation for my yc ahead of 30%. I'll do one for yc after and including 30%. I know this equation up here says it goes up to, and this is also greater than or including, but if we do this on our aerofoil, we'll end up with 2 points at the same place, and we don't want that. So we just got to make one bigger and one smaller then. So I now want m multiplied by 1 minus x, where x is greater than or equal to p. And then divided by 1 minus p squared. And then I've got the rest of this equation here. So it's going to be 1 plus x minus 2p. And now I've got this, I want to return yc. So when I've got this sub-function camber line within my greater function NACA 4, I can then use this to get my camber line. So I can say yc is equal to camber line x and p. Now if I run this, it's not going to do anything, it's just redefined this NACA 4. If I run this down here, it runs and it doesn't like it. Why does it not like it? It doesn't like it. So this error is telling me, it says operands could not be broadcast together with shapes 350 and 500. When you get an error like this, it goes up at the top is the line that I had trouble with. So you want to look at the top and see where it's had a problem. It tells me here, the first one that I recognize, it says, well, it's had a problem when it's run NACA 4 here. The next line down, it tells you within NACA 4, it's had a problem with this function. And then within this function, it said at line 26, it's had a problem. It says operands cannot be broadcast together with shapes 350 and 500. And that's because yc here, I've told it to only take the parts that correspond to x being greater than p, so i.e. the latter half of this, i.e. the bit from 30% chord aft. And so I was careful to make sure that I did the same with x here, but I didn't do the same with x here. So if I now do that there, redefine it, run this, this won't fall over, which is good. So I can now plot my camber line. So let's do make a plots. We'll do plt.figure. and I'll do plt.plots x, yc, and I'm going to make this a blue line. Run. Here we go. Ooh, does not like that. I've written down something wrong in one of these equations. That's giving me my Camber line. Let me just check that equation. X divided by 1 minus p squared. Let me just check this equation actually. I wonder if I've got this down correctly. Yep, that should be fine. Something's going on here. So again, I like to keep these mistakes in because it shows you how I know I've made a mistake and how to figure it out. What's going on here? So clearly the position, the Camber line's working ahead of this position. Now, have I got this equation in there properly? Let's have a look. So I've got m multiplied by, and rather than having c, I've got 1 minus x, which is because c for mine is minus x minus 2p. Oh, this is 1 plus x. That's why as well. God, I've done an awful job of copying this down. There we go. Okay, so this shows that I leave these mistakes in because they show how you realise when you make mistakes. But now we've got this equation in here for our Camber line. We are good. So we've now got the Camber line. I'm actually going to copy all of these into a screenshot, and then I'm going to be able to include this on my Okay, so we've got the Camber line now, and it looks kind of wildly curved. So what we can do is we can say we want to make the axis equal. So I'm going to do plt. I'm going to get the current axis.gca, which is a method, so I need to put parentheses around it. And then I'm going to do set ratio, I think. Set ratio equal. I think that's the syntax I need. No, it doesn't like it. It's not set aspect. I know it's set aspect. So there we go. Trawling back through my memory now. So we've got this aerofoil. That camber looks more normal. We're going to keep this line commented out for now because it's useful to see whether these curves are correct with these sort of crazy, very exaggerated scales. So this is going from 0 to 1 in the x-axis and 0 to 0.02 in the y-axis. Okay, so we've now got the Camber line. We now need to work out the thickness. So let's see what we've done here. So we need to work out the angle of the Camber line because we can get the thickness, but we need the angle of the Camber line to add the thickness above and below it. So let's bring the angle in. Okay, I've got my thickness up there. Let's move that away. Let's bring here we go. So we've got the expression that gives us we're saying here effectively the angle of the Camber line is equal to the arctangent of the first spatial derivative. If you've not taken too much calculus yet, don't worry too much about this because we're just going to code it up and use it. But now I'm then going to say I'm going to want some function that gives me theta. So let's say I'm going to say define theta, and that's going to be a function of x because it's got to be as a function of x. Let's call this theta funct x, and then I want it to be a function of m and p again because those are the two things that are in there. And we're going to use the exact same method that we did here previously. We're going to say I'm going to set my outputs to be a vector of the right size at the beginning. So I'm going to call this theta here. And then I'm going to use the exact same syntax, theta, theta, and I now just need to change these two expressions rather than being the ones that we put into the Camber line. I'm going to put the expressions in for the first derivative here. So 2 times m divided by p squared multiplied by 2 times p minus x, where x is less than p. And the second one is 2 multiplied by m divided by 1 minus p all squared multiplied by p minus x, where x is greater than or equal to p. Okay, so that's my theta. This one I actually need to spell as theta correctly, not theta. Actually, that's not correct because that's not theta, is it? This is dy by dx, so I'm going to call this dy dx here. And then I can say that theta is equal to np dot arc tangent of dy dx. And I want it to return theta. Okay, so I'm now going to do theta is equal to theta funct xmp. You might wonder why I'm putting these all into functions. It will become clearer when we try and do something smart a little bit later. So I've redefined this whole thing, and if I run this again, just check it doesn't fall over. It hasn't fallen over, so it's calculated this theta. And we're going to use this theta to help us plot our aerofoil, and we're going to use these expressions to get the upper and lower surfaces. Okay, but we need to have this expression yt. Yt is the thickness, and it's given by this number here, this big expression at the top. Move these out of the way. So we need to work out the thickness, which again, as you can see, it's a polynomial, so we can include that. So we need the thickness. Yt is equal to, let's write these numbers down. So I'll say A0 is 0.2969. I'm just going to write down these coefficients. Okay, so we'll call this A0, A1, A2, A3, and A4. This will just be a little bit tidier now. So now I've got these coefficients, and I can say that yt, remember I don't need to include c in here, I can say that yt is equal to t, which is the number I got from the top, so it's just my thickness, multiplied by 5, multiplied by a0 multiplied by x to the power of 0.5 plus a1 multiplied by x to the power of 1, I don't need to do that, plus a2 multiplied by x squared plus a3 multiplied by x to the 3 plus a4 multiplied by x to the 4. Okay, so that's my thickness, which means I can define my upper and lower surfaces. Okay, so I can now define that, and I can use this expression to get my upper and lower surfaces. I've got everything I need here. I've got x, I can work out my x and lower for my upper surfaces. So we'll say x upper is equal to x minus yt multiplied by np dot sine of theta, and then x of the lower which is equal to x plus that. And then we do the same for the y. Y of the upper is equal to yc, so that's the Camber line, plus yt, so that thickness, multiplied by np dot cosine theta. and y lower is equal to yc minus yt multiplied by np dot cosine theta. So let's see if we can plot these on as well now. So we're going to add them on as plots. So I'll do plt.plots, x upper, y upper, and I'm going to put that in red line. And I'm going to add the lower surface as green line. So I'm going to say, sorry, this should be xu and yu. And then this should be xl and yl. See if this works. I've redefined this, hasn't done anything yet. I run this. Oh, that doesn't work, does it? Something's wrong in this thickness equation. Something is wrong in one of these equations. Let's just, the first step is normally check these numbers. If you get any of these numbers wrong, it's real easy to mess this up. So let's just see what I've got. 0.2969 minus 1260, 0.3515, 0.2843, 0.1015. Okay, let's check I've got A0, A1, A2, A3 and A4, and I've got the correct coefficients. I've got half, 1, 2, 3 and 4. Okay, so that's correct. Might be the theta function then. And it sort of makes sense if it's a theta function because it looks like I've got some error occurring from the 30% point. So there's probably an issue in this equation. So let's compare this to my theta function. 2 times m multiplied by 1 minus p all squared multiplied by p minus x. Now that should be right. Alright, that's okay. Let's go back to the correct source actually. Right, there is a mistake in here. Mistake is not in the it's not in what I wrote down. It's actually that up here this should be a minus. Okay, so that's correct now. This one is a negative. I like to pretend this was a deliberate mistake left in there to test you, test me, but no. So if that's negative, let's go down here, take that one negative, try this again. We've got something that looks more like an aerofoil now. Okay, something that looks much more like an aerofoil. It looks pretty crazy, so if I put the axis is equal and then run this, let's just check. I still think that looks a little bit funny in the lower surface. So I'm going to put matplotlib notebook. That means I can scale this a little bit. So that's what's going on down here. Oh, so it's starting. Okay. Okay, the issue is I have written this equation down incorrectly as well. So there's an extra 2 in there. Get rid of this 2. Let's run this and run this. Ah, that looks well weird now. M on p squared. Oh no, I got rid of the wrong one. I got rid of the thing in here. I should have got rid of this one. There we go. Let's run this. Run this. There we go. Okay. So now we've got a nice smooth aerofoil with no discontinuities in the upper and lower surface. Took a little bit longer to get there than I would have liked. But I think it's important to show you where I make mistakes and how I'm able to notice that we've got through them. So we've got an aerofoil now that has been defined based on any sort of arbitrary NACA number. So I can try this again. Let's try a 0012. Okay, doesn't produce anything because these equations are expecting us to have this sort of theta expression in here. So what we can do in that case, if this doesn't work, then we can say, okay, we only want this to run if m is greater than 0. And if that's not the case, we'll say I haven't actually included the equations for an uncambered aerofoil. I can leave you guys to look them up in your own time if you wish, but we can just know that xu is equal to x, xl is also equal to x, yu is equal to yc plus yt, yl is equal to yc plus minus yt rather. So let's try and run this now. Let's see if this works for a symmetric aerofoil. Oh, it doesn't like it. Oh, I've got a good division by 0, so yes, we shouldn't do theta in that case. Okay, so let's go in here. I'm going to say that if m is greater than 0, then we can work out theta. Okay, so actually what I've done here, this bit change down here is now redundant, but I've made this change up here because it would have put out theta is equal to 0, and then sine of 0 is 0, and cosine of 0 should be 1. So this bit is sort of the same. So I can actually get rid of this line. Let's get rid of that. Run this again, and now I can run this down. Now I can get a symmetric aerofoil out of here as well. So we've got this. It would be good to be able to sort of check some of these aerofoils. So let's see if we can find some data about what aerofoils look like. A good place to go is the UIUC aerofoil database. If you just search for UIUC aerofoil database, you'll find a repository of lots of different aerofoils. If you search for NACA 4, there's both images of different NACA 4 series, so I can click on that, NACA 2421. Let's download this. So I'm going to take NACA 2421, I'll download that, and I'm going to save this to my data, NACA 2421.dat. Okay, we already know how to import DAT files. I can't easily show you this text file without messing around with my computer too much. Actually, let's do this. I'll just load it. So actually last lecture we learned how to load things. We learned how to load .dat files or .text files, anything that's a comma separated value, which is actually what these are. So if I click on here and show you, it's some form of text file which has the x coordinates and the y coordinates. This is actually in something called CLIG format. Oh, you guys can't see that. Let's I'll trust you to go to the website and look it up on your own. Okay, so we can import this aerofoil, and we can use the methodology that we used before from the last lab. So we can import data and then run it. So I'm just going to copy this out, and I'm going to put this down here. And instead of Cessna Drag Polar, the file that I just downloaded was called NACA 2421.dat. Now if I try and run it like this. I don't think it's going to work because it's not actually comma separated. So it's just going to tell me everything is just not numbers. So we'll try and see if it will accept a space as a delimiter, telling it that there is a space between every value. It's done this, it says, okay, I've got the X, I've got a bunch of spaces, and then I've got the Y. So it looks to me like there's 4 spaces between each data set. So I'm going to go up here and just put 3 more spaces in. There we go, and I've now got my 2 sets out. So I've got the NumPy array that's got X and Y data. So this is for the 2412, so let's go up here, say 2412. That's what I expect it to look like. And these data in this format are already normalized. So let's just plot it over as well. Let's do plt.plots data 0. First column, and I'm going to put data second column. Okay, that doesn't work. That's interesting. Is it 2412? Oh, mistake I made there is because the aerofoil is 2421, not 2412. So it's got the right camber line, but the wrong thickness. So let's run that. There we go. So we've produced an aerofoil that matches those data. It would be useful if we could take these data and work out what aerofoil it came from. Now, that's why I wrote all these as functions up here. So we're going to take a bit of a break now. I'm going to come back and record this next lecture a little bit later. So go through here, make sure you've got your own code that works. Now, what we did back in the previous lecture was we introduced a way to fit things. We imported something called curve fit from SciPy, and we then were able to say, I know my fit looks like drag model, and then I was able to work out what those parameters were to get a fit. So we're going to do something like that to this aerofoil. We're going to say, I've got these data. I know that my camber line looks something like this, and my theta function looks something like this. I'm then going to work out what this aerofoil must be based upon that. So I'm going to take a quick break. I'm going to record the rest of this, put it together. Make sure when you're up at this point, you have this notebook working, gone through and corrected the mistakes in it. So that's got to be out. Okay. And then make sure that you've got one that works, and we can use this to move forward and to do the next part, where we're going to be looking at taking those any of these aerofoils from this site, again any aerofoil that's a NACA 4 series, and use this to, again, this is how you find it. I searched for UIUC airfoil database. Any NACA 4 number we'll be able to use to work out what the aerofoil is. Okay, so I want you to pick one from here and use it. Okay, so we're going to be using that as we're going forward. Cool. So I'll take a break now, and I will get back to this a little bit later. Cheers, guys.